Okay, well, welcome back to a day without snow, and I've got Omar here. He's going to talk about his special office hours. You've got mine up here, but he wants to remind you some stuff here.
Good morning, everyone. Hope you guys have been doing well. I just wanted to remind everyone that I do have office hours. I mean, no one joins them, but it's probably a testament to Dr. Taylor's amazing teaching.
Right.
But in the announcements, I think it's the second one from the most recent. Um, I do say that I do host office hours Tuesdays and Thursdays from 11 to 1, but I am very flexible. So if you, I don't know, want to schedule like a personal one-on-one or something like that, I mean, I could adjust to your needs. And the link is the blue link labeled here. So yeah, I mean, I just wanted to remind you guys to make sure everyone knew that. And yeah, I mean, that's pretty much it.
So, like I said, you've got both of us trying to help you guys out with this thing. So, if you can't get a hold of me, get a hold of Omar. Like I said, he's got some special office hours listed up here. I've got my office hours listed up here as well. And on Tuesdays and Thursdays, if you basically shoot me an email and I get you a Zoom link as well during those virtual office hour type things here. I'm setting it up that you should be able to sign up for it, but computers are having issues over in Fretwell right now. So we're still working on upgrading some stuff over there in Fretwell, but I'll have that up for you guys pretty soon. But just shoot me an email, all you got to do, and I'll shoot you back a link on those Tuesdays and Thursdays. Mondays, Wednesdays, and Fridays, you can just come by my office between 11:30 and 12:30 over in Fretwell 335. I'm just sitting there just hoping somebody's going to come and ask me a cool math question. Otherwise, I'll eat lunch. All right, so I hope you enjoyed the winter sports of this past weekend. And it looks like we'll get another one this weekend, but it looks like it may be even snow in North Carolina this weekend. Yeah, until I actually see it, I'll believe it. I know. but just keep you guys in mind. A lot of other professors, they gave a bunch of virtual stuff and things like that to do. With you guys, I didn't send you guys to do anything except just to keep working on these particular problems. And I can let you know why. We are actually just a tad ahead of my course syllabi schedule, the course calendar. So I thought, well, I can either send you guys a crappy video of me doing this stuff, or we could just wait and do it on Wednesday, because the key to it is doing problems. I want you guys to catch back up. Now, don't just sit idly by, because you will fail this class. This is not an idly by kind of class, but you've got to work on these problems. So I wanted you guys just to take time to do the problems. You got all these wonderful WebAssign problems you got to get done. Don't hesitate. Don't wait till the last minute and stuff. So speaking of that, let's pick up what we did last time. So let me come over here and switch over share my screen. And we were working on section 2.4, exact equations. All right. And now look at our syllabus. We're going to do something weird. I'm going to finish up 2.4 today and then go all the way back to section 2.1. We reordered this stuff because we wanted you guys to start actually using your calculus skills and basically separation of variables, integrate both sides type thing here. These exact equations, those linear equations that we did, they worked your calculus skills. Then we're going to go back to 2.1 and talk about more visual perspective. So you'll see that part of today of something called directional derivatives and stuff. So these direction fields and the like. So, but just remind you, we were doing exact equations. Now, this is part of that Calc 3 aspect where you have some function z of f of x, y. And if you look at the differential of z, which is the derivative of this partial derivative of this function f with respect to x times dx plus the partial derivative with respect to y of this function times dy, this is your classic differential. So when you look at a special case of this function being equal to 0, when the differential of the function being equal to a constant, that is, the derivative of the constant is going to be 0, and you get this nice little special function here. Partial of f with respect to x times dx plus the partial of f with respect to y times dy equals 0. Now, in terms of the differential equations we're working on, and these things, again, are called exact equations, is we're giving you this differential form. This is what it's going to look like. M of xy times dx plus n of xy times dy equals 0. Now, if this m and n, if m was the partial of a function with respect to x, and the n was the partial of the same function with respect to y, then this would be called an exact equation. Okay, and that which means there's this overriding big function f of xy that's equal to some arbitrary constant c. So for the criterion for this to be a exact differential equation type, you got this m dx plus n dy equals 0. If this truly was the partial of f with respect to x, when you take the derivative of that with respect to y, something we learned in calculus 3, which most of you guys told me you have, but some of you haven't. It doesn't matter the order you do the mixed partials. You know, partial of function with respect to x, then respect to y, or take the partial of the function with respect to y, then respect to x. If it's a true function up there, they're going to be the same thing. And that's your check for an exact equation. You take the m, which is attached to the dx, you take the derivative of that guy with respect to y. You take the n, which is attached to the dy, you take the derivative of that guy with respect to x. If you get the same thing, they're an exact equation, which means you can actually solve this differential equation, okay? So just to remind you of what we did, so we started a problem last time, which was this one here, and I just got started on it before time let out. So, and I noticed the wording that I put on this one, solve if possible. And what I mean by if possible is this: if it is not an exact equation, then it's not possible based upon the concepts that we're learning here. This is a class called partial differential equations. We'll all go in an offshoot in a different way and show you how it may be possible to solve this guy using a bunch of other techniques, but you're definitely going to need a lot of Calc 3 for it, stuff like that. So we're only working with exact equations. So if it's not an exact equation, for us, it is quote unquote not possible. So here we go. I got x squared minus y squared dx is equal to 2xy minus x squared dy. Now, I wrote it mixed up. Watch for that. It's all about algebra. This is not in your classic differential form, which is m dx plus n dy. I got m dx is equal to something n dy. So to get it to the equal to 0, you pull everything to one side. So I subtracted the minus and subtracted this whole term. 2xy minus x squared dy. But when you subtract, that negative is going to distribute. And this is why I set you guys up before we left last Friday. And so that ends up giving you minus 2xy plus an x squared. Just looks better to put the x squared, positive x squared up front, minus the 2xy, and put parentheses around that. There's your dy. Now, here's the question. Is this, now it's in the proper form, an exact equation? Well, to be able to figure that out is I got this m part over here, which is I'm saying x squared minus y squared. And I got this n part over here, which is the x squared minus 2xy. Again, it's in my proper form here. And I'm going to do this. This is attached to x, so I'm going to take the derivative of m with respect to the other variable y. And again, to remind you guys, that especially you guys who haven't had calculus 3, you're focusing on a single variable, and all other variables are considered to be constant. Constants hold over, and when they're by themselves, the derivative of constant is 0. So the derivative of x squared with respect to y, well, there's no y in it. That's going to be 0. Minus what's the derivative of y squared? 2y. So I end up getting this to be equal to negative 2y. Now, come over here. This is your n. I'm going to take that, the partial of n, and take derivative since it's attached to the dy. I'm going to take the partial of n with respect to x. Okay? What is the derivative of x squared? 2x. Minus what's the derivative of 2xy with respect to x? 2y. Derivative of x is 1, and the constant 2 and the y stay there. So I've got the partial of m with respect to y is negative 2y. The partial of n with respect to x is 2x minus 2y. They are not the same thing. You with me? So this is not an exact equation, which means not possible to solve using techniques shown. Does that make sense? I'm not saying it's not possible to solve this type of thing, but that's require the PDN class. We're just talking about the techniques we showed you guys on how to solve an exact equation. If it's not an exact equation, you're just supposed to say not exact equation and move on to the next problem. Okay. Just want to show you one. It says I got a bunch of them on WebAssign that are listed up there in the first section of them. Are these exact equations? Yes or no? Okay. But then we throw this at you. If it is an exact equation, just go ahead and solve it. If it's not, just say not. Okay. This one would be a not. So let's make them even nastier. Try this. Again, solve if possible. This one, I went ahead and put it back into the standard differential form, differential equation. I've got x plus 2y divided by x plus y dx plus the natural log of x plus y divided by x plus y dy equals 0. So in the present form, I can tell you that my m part is the x plus 2y over x plus y, and the n part is the natural log of x plus y over x plus y. You with me? All right, enjoy. Now, the only way it's possible to solve this, guys, you got to show me this thing's exact. So that's the question here. Is this going to be an exact equation? Question mark. So I've got to take the m, the derivative of the m with respect to y. See, it's attached to the dx there, so you can see it. It's attached to the dx. So you take the derivative of this guy with respect to y. So it makes it the mixed partial there. All right. How do I do that? The function is x plus 2y divided by x plus y. I want you to take derivative of this guy with respect to y. What rule do I have to use? Quotient rule. Trying to bring back a bunch of Calc 1 and Calc 2 stuff with you guys. Quotient rule. Derivative of the top times the bottom minus the top times derivative of the bottom all to the bottom squared. Derivative of the top with respect to y. Derivative of x plus 2y with respect to y is 2. Derivative of the top times the bottom, x plus y. Minus the top, x plus 2y. Times derivative of the bottom. What's derivative of x plus y with respect to y? Well, derivative of x would be 0, derivative of y would be 1. All over the bottom, x plus y squared. Does that make sense? State them up. So I would distribute here, that'll be 2x plus 2y. That times 1 doesn't matter, but that negative is going to distribute. That'll be a minus x minus 2y over x plus y squared. And let's see what we end up getting here. Here, the 2 y's cancel, it looks like to me. And I got a 2x minus x, which makes the derivative of the m part with respect to y equal to x over x plus y quantity squared. Does that make sense? Okay. Now wait. Now, try this guy. The other side. We want to take the derivative of n, partial derivative of n, with respect to x. So n over here is natural log of x plus y over x plus y. All right. We're going to take derivative of that guy with respect to x. That means y's are considered to be constant. Now, what's the derivative of natural log of x plus y? So this would be chain rule, though. It'll be 1 over x plus y times derivative of the inside. Derivative of x is 1. Derivative of y is 0 times 1. Plus, what is the derivative of y over x plus y with respect to x? Well, 2 ways I can do this. I can either bring this guy to the top and make him x plus y to the negative 1 and use the chain rule on him. Or I could use the quotient rule. Which one do you want me to use? Well, you get the same things. You guys that want to do the chain rule can do it that way. I'm going to use the quotient rule because you guys asked, because it's kind of lame here. We're taking rid of respect to x. What's rid of y with respect to x? So it's rid of the top, which is 0 times the bottom, x plus y, minus the top, y times rid of the bottom. What's rid of x plus y with respect to x? 1. All over the bottom, x plus y squared. Agreed? Clean them up. So that gives me the partial of n with respect to x would be equal to 1 over x plus y plus 0 times anybody is gone minus y over x plus y squared, right? Okay. Here we go. Let's add them together so we get the common denominator here. So getting the common denominator would be x plus y squared. So I need to multiply this guy by x plus y. What I do the bottom, I do the top. So it'd be x plus y up there, plus a negative y over x plus y squared. Now, together, common denominator is x plus y quantity squared. So all you got to do is add up your numerators. What is x plus y minus y? X. And lo and behold, they're equal, which means it is an exact equation. I wanted to give you one that was a little more meaty, if you will, made you work at it a little harder, which means this, to actually get the actual answer. Because this m part right here was attached to dx, to get the active function, the m part, which is now we know being exact, is the partial with respect to x. The m part, which is x plus 2y over x plus y, you want to integrate with respect to the x to actually get the function back again. Okay? This is the m part. We now know being exact, it's a function partial derivative with respect to x. So I'm going to get this guy. How do I do that? Well, because I have two terms in the numerator, I'm going to separate them. This will be x over x plus y. Okay. Plus 2y over x plus y. Integrate with respect to x. Okay. You with me so far? Okay. All right. So well, I can clean this up a little bit better. Because integrating this guy, you know, can you do an antiderivative of these guys? With respect to dx there? May I make a suggestion? Again, I'm showing you tricks of the trade on this one. Look at your denominator. It's x plus y. Instead of doing it this way, which would be harder, try this. X plus 2y, instead of breaking it up, why don't you do it this way? This would be the integral of x plus y over x plus y. Because this was going to be a pain. You got to do, you can do substitution, and then you got du, and you have the extra x left over. You can do an integration by parts, or you can go and substitute. It becomes a pain. But looking at this, all I did was do 2y is y plus y. It's all because of that denominator, x plus y. So this would be the integral of, watch this, very impressive, x plus y over x plus y plus y over x plus y dx. What is that? 1. Integral of 1 plus y over x plus y. Does that make sense? So this one was not the way I would go about doing it. I would do it this way. It's all because of the denominator. You got to think about the tricks on these things. It can get difficult. I'm giving you a more advanced problem is really what I'm trying to do here. However, what is the integral of 1 with respect to x? X plus what's the integral of y over x plus y with respect to x? All right, I'm going to come over here and just to show you this guy. I'm going to put him down here. The integral of y over x plus y with respect to x. I'm going to do u substitution. I'm going to let u equal to the denominator, x plus y. My focus is on the x's. So what's du? What's derivative of x with respect to x? 1. What's derivative of y with respect to x? Dx. So this one ends up giving you the integral of, this was u, and the dx is actually du, and y is a constant. It just stayed there. With me? So that's the integral of what y times the integral of 1 over u to u, which is y times the natural log of u, which makes it y times the natural log of x plus y. So y times the natural log of x plus y. This would be what my function is, but plus a constant. And by the way, what are constant variables also attached to? Just regular constants, but what also? We integrated with respect to x, which meant y's were constant, right? So don't put the little put in parentheses, y's we consider constant there. So that is almost my answer. That's integrating the m part, which is the fx. Now let's come over here and integrate the n part over here. So here we go. The fy, the n part, which is fy, is equal to this natural log of let me see here. Natural log of x plus y. And just recopy it. Plus y over x plus y. Now, what are we going to have to do here? All right, well, yeah, but man, do you want to integrate this guy? So what you're telling me is to get f back again. I'm trying to show you guys some tricks here. The integral of this dude here, fy dy, which is equal to the natural log of x plus y over x plus y. We're going to integrate that guy with respect to y. It's nasty. You want to integrate this guy? Well, then what else? But note, we already have this. F, which was equal to, what do we get for f integrating the first guy? We end up getting what? X plus y times the natural log absolute value of x plus y plus that constant in terms of y. That's what this guy is supposed to be equal to with some kind of extra constant. We got to figure out what the constant has to be. Okay? So this is a function of y here. So what if I did this? Remember this. Instead of integrating this guy, another technique is take this guy and take the derivative with respect to y. Would you rather integrate or take a derivative is basically what I'm asking you. I'd rather take a derivative, all right, with respect to y. So this is, remember, I got this guy from, I took the f part, the easier part here, and I integrated him. This is where I got him from over here, okay? I integrated him out. Now, got this. So if I take derivative of this guy with respect to y, he should be somewhere close to this thing over here. So let's see what we got. So when I do that, what is the derivative of x with respect to y? 0 plus what is derivative of y times the natural log of x plus y? And what rule would I have to use to take derivative with respect to y? Product rule. Derivative the first times the second plus the first times derivative the second. Derivative first. Derivative of y is going to be 1 times the second natural log, and I'll just put parentheses here, of x plus y, plus the first x times derivative the second. What is the derivative of a natural log of x plus y with respect to y? That's going to be 1 over x plus y times derivative of the inside. Derivative of x is 0. Derivative of y would be 1. Does that make sense? Cleaning it up, that tells me fy is going to be the natural log of x plus y over x plus y. Does that make sense? And notice what I end up getting here. I end up getting the exact same thing, which tells me when I looked at f, back at looking at f, which was x plus y times the natural log of the absolute value of x plus y plus c of y. But if I got the same thing, there's no extra y's left over. Does that make sense? Which means that this is not just a constant term for y. If I did, I would have seen an extra y show up in this thing. I don't, which means my function f is actually just going to be x plus y natural log absolute value of x plus y plus arbitrary constant, not a constant with y's in it, because when I took my derivative, there were no other y's in there. And okay, so if you think about this, and I can another way I can describe this, you took derivative of this guy, right? You took derivative of this guy. There it is. What plus? Wait a minute. Take derivative with respect to y. What is derivative of a c times a c of y? It's going to be c prime of y. But that would mean that this c prime of y, since you went right back up here, plus this c prime of y, there's c prime of y is actually equal to 0 because there's no other y terms in this particular part. So if c prime of y is equal to 0, that way when you integrate both sides, integral to 0 is just going to be what? That c of y would have to end up being just an arbitrary constant. I tried to argue my way out of it, but that mathematically it makes sense. There's your function. So you can get these guys to be rather tough. Now, I taught you guys last time that basically you take the m, once you find out their exact equations, you take m, integrate respect to x, you take m, integrate respect to y, if possible. It means sometimes we have to integrate one of them. And maybe you can take that answer and then take derivative with respect to the other variable, and the other function should show up, but you have to check out your constants. So there's other ways of juggling this stuff. But these are called exact equations. So let me do one more, only because now that I've got you guys completely bamboozled on this thing here. Okay. And so officially, therefore, remember what we said before. How do we like to write the answers on this particular problem? The f of x, y, we like to set equal to the constant. So the answer they would have in the book would be x plus y, natural log absolute value of x plus y would be equal to the constant. Just move the constant to the other side, if you will. And a negative a constant, still a constant. That's how we typically write our answer. All right, and I got one more for you, but only because I'm just mean. Okay, let's see here. Whoa, wait a minute. Dr. Taylor typed one up. No, I didn't. I copy, pasted it off a WebAssign. This is one of your homework problems. Okay. Just wanted to show you guys that I'm not just making up this stuff. I'm actually going to do something with it. But they threw a curveball at you on this one. What did they do? And they said, solve the given initial value problem. Well, not just that. They did 4y plus 2t minus 7dt is 8y plus 4t minus 1 dy equals 0. They switched out the letter. Instead of putting x's, they put t's. Okay? So, but it's still in differential form. And we got an initial condition. So if it's possible to solve this guy, not only will I solve it, I'll actually figure out what that C is. That's what the initial condition job is, okay? So we got one extra step on this thing. This one looks a little easier than that natural log thing I just played with, so let's take a look at it. So this is in the form of m dt plus dy is equal to 0, okay? So we're going to take m, and we're going to take the derivative of that guy with respect to the other variable, dy, and then we're going to check by taking the derivative of n with respect to the other variable, dt, and let's see if we're going to get an exact equation, okay? So just to remind ourselves, m was equal to the 4y plus 2t minus 7. What is the derivative of m with respect to y? What'd you get? 4. Okay. 4. Derivative of 4y with respect to y will be 4. Derivative of 2t, there's no y's in it, 0. Derivative of minus 7, there's no y in it, 0. All right, and n over here is that 8y plus 4t minus 1. You with me? What is the derivative of n with respect to t? 4. 8y, well, there's no t in it, so that's 0. Derivative of 4t is 4, and minus 1. And notice they're equal to each other. Bingo. Boom. It's an exact equation. So to get the big F function, we're going to integrate the m part, which is really a function of with respect to t now instead of x's, dt. And to also get f, you can integrate the n part with respect to y, because this n is actually a partial of f with respect to y. So here we go. So let's check out f. F would be the integral of the m part, which is the 4y plus 2t minus 7 dt. With respect to t, focus on t's, which mean y's are constant. What's the integral of 4y? Very, very good. 4yt plus what's the integral of 2t with respect to t? 2t squared over 2. The 2's cancel. You're left with t squared minus what's the integral of 7 with respect to t? 7t plus c, which are in terms of y's. Y's are also there because they're considered to be constant as well. Now, there's my f. I could take derivative of this guy like I did in the last one, or because these guys are so nice, let's just integrate the second side over here. F would be the integral of the n guy, which is your 8y plus 4t minus 1 dy. So, what's the integral of 8y with respect to y? 4y squared. Very good. 4y squared. 8y, y squared over 2. 2 goes in 8, 4 times 4y squared. Plus, what's the integral of 4t with respect to y? 4ty minus what's the integral of 1 with respect to y? Y. And then plus a constant. And constants are now with constants in terms of t's. So now combine. So what would your f function be? Well, look at the first part. 4yt. 4ty. Yep, that's the same thing. I was like 4ty. Looks better like that. Okay. So they're gone. I got to have a t squared plus t squared. Well, that's part of this guy here. Okay. Minus 7t. That's got to be there. That's part of that function over there. So they're now gone. And coming over here, I got to have a, in terms of y, plus 4y squared and a minus y. All the parts are there, which leaves me with just one big constant with no worries about t's or y's being constants now. You see what I did there? I went through and grabbed this whole part, and then the parts that weren't here, I grabbed those over here. So both of them are actually represented, plus c. But wait, there's one more condition here. Remember that y of -1 is equal to 2, okay? with the initial value problem type thing here. So remember how we talked about this. Before I plug that in, how do we put this particular equation? How would we write the answer? We write it like this. 4ty plus t squared minus 7t plus 4y squared minus y, and we set it equal to the constant. That's how we write our standard equation solution. Does that make sense? But now, plugging in this information, and that's a semicolon there, all right? This tells me that t is -1 when y is 2. So let's see what the constant is going to be. 4 times t is -1, y is 2, plus t, which is -1 squared, plus, or minus actually, minus 7 times t is -1, plus 4, y is 2 squared, minus y is 2. That's got to be what the constant is. Does that make sense? I plugged in t is -1 and y is 2, chunked it in here. Now clean them up. -1 times 2 is -2 times 4 is -8. -1 squared is +1. Minus 7 times a -1 is a +7. 2 squared is 4. Okay. And 4 times 4 is 16. Plus 16 minus 2 equals my constant. -8 plus 1 plus 7 cancels, right? -8 plus 8. 16 minus 2 is what? 14. 14 equals C. Therefore, your particular solution to this problem is going to be 4ty plus t squared minus 7t plus 4y squared minus y equals, and the constant is 14. There's my answer. And again, I stole this one off of your web assign, so let you guys know if it's an exact equation, solve it. And they gave you the initial condition so you can figure out what that C is that it's equal to. Does that make sense? All right. Well, we're moving backwards, as I promised before, because we skipped over section 2.1, but only because I wanted you guys to get into solving some actual differential equations, and some of them in differential form. But I want you guys to get a feel for, actually putting your calculus involved before we start talking about visual perspective on this thing. So we're going to talk about direction fields, okay? So a direction field is a graphical representation of a solution to a differential equation. It's a visual thing, okay? Now, the best way for me to describe this thing to you, because I'm going to go old school and talk about basically what these things mean. So this is my classic X and Y. So I've got this example, and the best way for me to describe this is actually look at it as an example. I got dy over dx equals x times y minus 1. Now, let's talk about this. Dy over dx is equal to the slope of the tangent line. We're going back in Calc 1, good old days. Slope. It's a slope. So, and the x and y's are points. So when I'm going to be doing these direction fields, I'm going to be looking at a graph where we're looking at a bunch of points, x and y points. And every x and y point, there's going to be a slope. So let's talk about the slope of the tangent line. So if dy over dx equals 1, what does a 1 slope look like? Rise over run. It's a slope. Rise over run. It is an actual 45-degree angle from left to right going up. Does that make sense? Similarly, what is dy over dx equal -1? What is that going to look like? A -1 slope. As you read it from left to right, it's still a 45-degree angle going down -1, down 1 over 1. Just curious if I gave you dy over dx is equal to, I'm gonna make up a number like 4. What would that slope look? What's a slope of 4 gonna look like? See, exactly. You got to rise 4, run 1. So it's a little bit steeper, right? Does that make sense? But if you want it to be exact, go grab a computer and program this mess into it. We're not, but I'm just telling you, it's a little bit steeper. What about this one? dy over dx is equal to a negative 1/2. What would that look like? A negative 1/2 slope. It's a negative slope, so we know it's going to go down, but you go down 1 over 2. So it's not quite steep. Does that make sense? As compared to these guys here. And wait a minute, I got a better one for you. What about dy over dx equals 0? What would a 0 slope look like? What kind of straight line? A horizontal straight line. Right. It's a horizontal straight line. With me? One more. dy over dx E. Now, you guys know me, and you've had me in most of your classes in math. What does D and E stand for? Does not exist. What's that? Does not exist slope look like? Vertical. Vertical lines don't have slopes, right? And you could put arrow on top or bottom. I don't think it really cares. Okay, it's a vertical line. Does that make sense? Okay. So this is the game plan. So remember my example? That's why we have an extra sheet of paper over here. So let's take a look at the example. Here we go. dy over dx is equal to x times y minus 1. That was my problem. Okay. Now, if I was going to do this thing here, first thing I'm going to do is I'm going to do 2 things. I look at it as a fraction. I'm going to set the numerator equal to 0, and if it does have a denominator, I'm going to set it equal to 0. Numerator equals 0 means I'm going to have a derivative equal to 0. That's horizontal lines. I'm going to define where my horizontal lines are and my vertical lines. There's no fraction on this guy here, so there's not going to be no vertical lines on this thing. So if I set it equal to 0, that would be the horizontal slope. Does that make sense? Now, this is an equation. If 2 things multiply together equals 0, that means either x is equal to 0 or the y minus 1 has got to be equal to 0. And if you solve that, that would mean y equals 1. So I'm going to come over here and I'm going to graph x, y. Okay, and I'm going to put some hash marks on here. You know, just 1, 2, 3, 4, 1, 2, 3, negative 4. 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. You understand? I'm doing this by hand. You want it more exact, you live in the 21st century, we can go and get a program on this thing, and it'll slap this thing up. What's that? Really?
Yeah.
What'd you use? Chat GPT? Built in. AI. It'll be the death of us. Okay. Okay. Well, we're going to go old school. I'm going to show you how to do it by hand. Chat GPT crap. Okay. All right. So there's 2 lines right here. There's x equals 0. Can you please tell me what x equals 0 looks like? X equals 0. If x equals 0, that is also known as the, no, well, not just that. It's the y-axis, right? And look at the y-axis. X equals 0. It's a vertical line. So on this vertical line, at every point on this vertical line, I'm looking at the dots here, you're going to have up and down, okay? You are going to have little horizontal tangent lines. So I'm just going to put a little dash right there, horizontal lines. Does that make sense? That's your x equals 0. They're going to be little horizontal dashes. But wait a minute. What about the line y equals 1? Y equals 1 is also going to have a horizontal dash. Y equals 1 is right here. So this would be, I'm putting these little points right here. Y equals 1 is a horizontal line. And notice I'm just putting the dots at the points, but officially it's on any point on this line. And so these are also going to have little horizontal lines. Now what this does for me is it subdivides my graph into sections. X equals 0, y equal 1, and they're the horizontal lines. Does that make sense? So now I'm going to come over here, and I'm just going to plot points in every little area. Plot point and tell me what the derivative is going to be. And the beauty of it is this. You don't have to plot a bunch of points, because if they're not zero and they're not, does not exist vertical, they're either going to be all be positive or all be negative. They're all going to kind of go in the same general direction. They may be a little steeper than others, but here we go. So if I plot points like right here at 0, x equals 0, it doesn't matter what y is at all. When x is equal to 0, you get a horizontal line. So it's horizontal right there. Okay. And I can also simply for anything. And also with y equals 1, x can be anything. When y equals 1, you're still going to get a horizontal tangent line. You're going to get a 0 slope, basically, is what I'm telling you here. Here's the numerical value of it. But now I'm going to come over here. Let's plot a point over here. Let's say it's the point 2, 3. I'm going to use that point right there. X is 2, y is 3. What would your slope be? Plug it in. X is 2, y is 3. 3 minus 1 is 2, times 2 is 4. I don't care what the number is. I want to know what kind of slope it is. What's the slope of 4? Going up. So at that point, it's going up. Does that make sense? And I'm not being elaborate. It's a little bit steeper than others and stuff like that. But all in all, they're all going to be going up in this little section over here. So you can sit there and plot all these little points around it, put little dots wherever they're at, and they're all going to be going up. Now, the closer to horizontal is, they're probably going to be a little more horizontal down here, and then they're going to be horizontal up here, and then it's going to be more steeper and steeper and steeper and steeper, but it's still all going in the same direction. Does that make sense? I'm not caring about what the actual number is. All I want is the flow of it. And that's what you're getting, is this these directional fields that give you a flow of this thing. All right, wait a minute, keep going here. Let's pick another point, like maybe down in this quadrant somewhere, like the point 2, -3. X is 2, y is -3 is right here. Now there's a bunch of points around here. There's even these points right here. All right, so here we go. 2, -3. What's going on there? X is 2, y is -3. -3 minus 1 is -4 times 2 is -8. It's big time negative, very steep negative. Does that make sense? So it's negative here. And in this whole area, it's still going to be negative. Does that make sense? And all I'm doing is putting a little negative slopes here. Now you could put it right here on 1, when x is 1, and for example, x is 2, y is negative, y is 0, sorry, 2, 0. I'll just do that one just to show you. 0 minus 1 is -1 times 2 is -2. Still going to be a negative slope there. So it's a -2 slope. So yeah, it looks like that. Does that make sense? I come over here someplace, and again, I'm just picking on the 2s and the 3s type thing here. So I can put -2, -3. Plug it in here. -2, -3 minus 1 is -4. -4 times -2 is a +8. So it's back over here. So at -2, -3 at this point, it's a +8 slope. So this would be going up this way. So all these points over here are all going to have these positive slopes. Does that make sense? And then these will be the same. And then the last one is put 1 over here. And here's the deal. What would this be? Like -2, +3. -2, 3 right here. X is -2, 3. 3 minus 1 is 2. -2 times 2 is a -4. Back to a negative slope. So this would be a negative slope here. So everybody in this region, at every one of these points, it may be a different number, but they're still going to have the same sign. It's going to be negative. So they're all going to have those negative slopes to it. Does that make sense? And what this does, it gives you a flow for this guy. This is why I'm trying to show you. Remember that initial condition? The initial condition actually tells you what the exact equation is. This is your flow chart. For example, right now we got storms coming in here, and we got wind blowing in from the north. making it very cold here. If you look at the little maps, it's directional fields because they figure out where you're at and where the wind's blowing. They have these little points where the wind's blowing this way, and it comes down, and then it's going to flow up this way. So the initial condition on these guys, this is called the directional field. Okay. And if you want to see some exact equations, is you pick like an initial condition, like for example, right here. And then you go with the flow. Okay. So before over here, I must have come down with the slope. I hit this point horizontal here, and then it's going to come up. If I hit this point right here, I'm going to go completely horizontal. If I use this as an initial condition, before it, I'm going into this point, so I got to come in this way, and then I hit this point, and then my flow chart is going to flow me out this way. Does that make sense? And it depends on the initial condition, which one of these three different equations or more you can have. So you can sit there and draw out the actual, solutions for this thing. So right here at 1, it was horizontal, okay? But up here, it could have looked like this, look like this. Down here, it was going to look like this or look like this. It depends on the equation. Here's your x-axis, here's your y-axis. And that shows you also how important the initial conditions are about which type of equation your solution is going to have. It'll be either upside down parabola if you're down here, or a right side up parabola if your initial condition puts you up there. Does that make sense? So, and I haven't solved the differential equation yet. I just gave you a differential equation just to get a feel for what the different types of equational solutions you could have based upon the picture. Does that make sense? That's why the importance of these directional fields. We'll do more next time, and I'll actually work on this problem and solve it for you next time. But we're out of time, so we'll do that on Friday. See you guys then.
Well, I like the chart.
Yes.
Yeah.
Yeah.
Yeah, look at that.